AC 111 lecture 14, set 5. We are going to talk more about the final project and how that is going to be computed and reported. Here, we need to have a, files transcript 1 and transcript 2 text. And these text file will have copy of the model simulation results. So we have the task bench that is given, and then you need to run this test bench, and after you run the run all command, you have to save your transcript by going to the file menu and clicking save transcript as. And I'm sure once you work with ModelSim, this is very, this is basically what you do with any other file system when you try to save the output results. And the good thing is the transcript file contains a history of all commands used in the current ModelSim session. And then, you could clear this and make sure that every time you generate a transcript file, you are generating it for the session at hand and are including it for that. And, as you will see, the ModelSim will have different parameters and values generated in the file. What we are going to use is we are going to use the total number of cycle for your cycle count, and that is the value that should be reported for your final project. Now, we also need this message 1 text and message 2 text, which is a copy of the Quartus compilation messages. You need to make sure that your design compiles okay. And then you could actually save these messages by right-clicking the message window and choosing Save Message. And it's important. The reason we want you to report these files is that we want to make sure that you don't have any hazardous situation, no warning about latches or additionally inferred latches because you didn't design a fully synchronous design. So make sure that you include these files in your submission. Now, we need to also have some report about how this fits within your device. And again, this is a virtual simulation. This is not an actual device, but you need to make sure, because we are synthesizing it into a hypothetically simulated device, I need you to make sure that you select the right device for your compilation, and make sure that the total block memory bits is 0 when you're doing this. And then this report tells us how much area you're consuming on the real estate of this simulated chip that they have in their environment. So you basically just need to make sure that you're selecting the right device, and the simulator is doing the rest for you. Now, in your Bitcoin hash.fit, it must say that the total block memory bit is 0, which means, sorry. Sorry. Which, otherwise this will not pass. And then if this is not, if this is not the case, go to this assignment settings and then go to compiler setting, and then turn off these knobs to make sure that you have the right setup for your simulation. Then again, as I mentioned, we don't want this latches inferred. So, this is could be caused by many different things. Maybe you will have a bug in your system, or you could have some replacement. Make sure that you turn off these. And if you still have inferred mega functions, you need to contact us or the TA and make sure that you have this, because your design would not pass if you have this inferred mega functions. And the design, again, will not pass if you have inferred latches. Make sure that you have that. And now, again, we are talking about the design, we're talking about optimization, and the optimizations we were concerned with were the area and the delay. So we need both the area report, which we just mentioned, but also the timing report. And, in order for having a good timing report, you need to make sure that you use the correct Fmax, and you have one clock, which is the only clock. So if you have multiple clock domain, it could create trouble. Make sure that your memory is clocked with the same clock, and your functions, which is for static timing analysis, it must show CLK as the only clock for the system. So here again, you do the selection and you have only one clock assigned, and that should be done. Now, last but not least, and something we will go through in the next slide set, is making sure that we don't have this huge WT array all instantiated, because if one way to do it is to have a very inefficient design, that you have this kind of 64-bit words, and then you have 64 bits in the memory, and then you have each of them is 32-bit word, and then you kind of try to do this. Basically, this generates a huge 64 by 32 array, which will use a lot of real estate on your chip. And if you remember from the cycles of the SHA-256, not all the elements of the WT are going to be multiplexed and used in each of the cycle. In fact, what we will see in the next one is, we kind of see that, if you just, every time you kind of try to read from this W's and put them in the right register, the right W's in the registers, you don't need to multiplex so many things into your function and generate this huge overhead. And that's the trick we're going to use to optimize things. So we are going to set a pipeline, and this pipeline is going to put in every time we just take a memory word that is appropriate for that round, we are going to read it, and this is basically a good guide for you how you read. And then every time we read this memory word for that T that we are at, and then we set the memory address to T+3, and then that can help us every time we are reading, we only read that portion of the memory that is used for that cycle of computation, and we are not trying to multiplex everything in this huge 32-bit by 64-bit function and try to use it. Okay, so the delay optimization that we are doing for the sequential is basically trying to pre-compute some of the WTs and pipeline them. But for the parallel case, we want to make sure that we can compute this 16 nonces in parallel, and but the caveat here is making sure that your design is small enough that you can fit 16 of them to run in parallel. So your goal, especially for the parallel case, should be to have as small area for each of these nonce computation as possible, so we could fit all 16 of them into the body of what we have, which is pretty limited. And if you do this not carefully, if the design is too large, it will fail during the fitter, and it says just it can't fit the thing on the device. So one of the ways to try to do this is doing it stage by stage. First, you do it for less number of nonces, say 4 nonces or 8 nonces, and then slowly try to increase the number of nonces till we get to the right value. Okay, next we will be talking more about the optimizations and how we could do this better.